Photoelectric effect. When electromagnetic radiation incident on some materials, they emit electrons and hence produce EMF. This effect is called photoelectric effect. Let's imagine we have some photoelectric material A. Now we are going to produce EMF attacking material A by electromagnetic radiation. Let's start with lowest frequency electromagnetic radiation and gradually increase the frequency. Here we can realize that the electron emission starts only when the frequency of incident radiation reaches to a particular value. That particular frequency is called threshold frequency. Immaterial of the intensity of the electromagnetic radiation, no electron emission occurs by a photoelectric material if the frequency of incident radiation is lower than the threshold frequency. Threshold frequency is denoted by F0. Now look at this circuit. This is a photocell, ammeter, voltmeter, a variable voltage supply including negative values by means of potential divider principle. Now let's imagine in this situation, photocell creates some EMF. By this external voltage supply, opposing voltage is provided. We can gradually increase this opposing voltage from a very low value until the current in the circuit becomes zero. Value of that opposing potential where the current driven by the photocell becomes zero is called stopping potential. That potential is equal in magnitude for the EMF generated by the photocell. If we plot the IV graph for this circuit, we will get a graph as follows. The bottom line represents one intensity of light, top line represents greater intensity of light. Two graphs in the diagram represent two different intensities of lights. If we plot several IV graphs for several intensities of lights, we can realize that stopping potential does not depend on intensity of light. Using the same experimental setup, we can do another experiment. This time, let's keep the intensity of light constant and let's gradually change the frequency of incident radiation starting from very low value. Studying the graphs relevant to such an experiment, we can realize that stopping potential increases with the frequency of incident radiation. The frequency of incident radiation at which stopping potential becomes zero is the threshold frequency for particular material. This variation is represented in following graphs. In the first decades of 20th century, photoelectric effect had been identified, yet the existing theories of classical physics could not explain this behavior. Only Albert Einstein could theorize the photoelectric effect by means of Max Planck's quantum theory of radiation. According to Einstein's theory, some minimum amount of energy is required to release the electrons from its bonds. This amount of energy is called the work function, denoted by phi. If the Threshold frequency is F naught, phi is given by HF naught. Einstein's complete photoelectric equation is as follows. Here F is the frequency of incident radiation, phi is the work function, K max is the maximum kinetic energy achieved by the photoelectrons. This equation can be rewritten in different forms as follows. Here F naught is the threshold frequency, ME is the mass of an electron, V is the maximum velocity achieved by photoelectrons. If the equation is written in this form, E is the electronic charge, Vs is the stopping potential. Einstein's photoelectric equation can be rewritten in all these three forms.